What's up, guys? Let's go through another example from optimization. You want to build a cylindrical bucket that can hold 36 ounces, that minimizes the amount of material being used. What should the dimensions of the bucket be in inches? So we want to start off with our picture. So I have a cylinder here, and I can go ahead and I can label my cylinder with some variables. I'm going to use R for the radius, and I'm going to use H to represent the vertical height of the cylinder. Now, one thing that's a little bit different about this problem is that it mentions that the cylindrical bucket can hold 36 ounces, but that we want the dimensions to actually be in inches. So we need our units to be the same. We can't work with both ounces and inches. So just off to the side, I calculated that 36 ounces is approximately the same as 65 cubic inches. So we just want everything to be in terms of cubic inches. So that way all of our units will match and we can proceed with the problem. And I just looked that up. You'll be given conversions like that if you actually have to use them. So we can disregard the 36 ounces. We don't care about that anymore. We're going to proceed working with our 65 cubic inches. So let's set up some equations. As you guys have seen with optimization, you need two equations. In this case, we can work with volume. Volume is pi r squared h. You can look up these geometry, volume, and surface area formulas. I don't expect you to know them. Surface area for a cylinder is 2 pi r squared plus 2 pi r h. And actually, in our next unit, we're going to see how these formulas are actually related to each other. If you think about derivatives, there's a connection between volume and surface area. So what are we trying to optimize? Well, we're minimizing the amount of material being used. So if we're minimizing surface area, we want the surface area equation to have one variable. Now, some people might say that there's three variables right now, but you have to remember that pi is not a variable. So our variables so far, we have the r for the radius, and we have the h for the height. So we can either swap out both of the radiuses, or the radii, I should say. We can swap out both of the radii, or we can swap out the one height. So I'm going to swap out the one height. I'm going to set my volume equation equal to 65, and then solve for the height. And remember, we're using the 65 cubic inches, not the 36 ounces. So I get h is equal to 65 over pi r squared, and now I'm just going to plug that into my surface area equation. So this process should seem pretty similar to what we did with the box problems from the first assignment. So I'm just doing that same substitution step here. Of course, the algebra is getting a little bit more tricky, as you guys will see as we go forward. So I plug in my 65 over pi r squared, and now I'm just going to go ahead and simplify my surface area equation. And it does simplify very nicely. You have your pi's that cancel out on the top and the bottom, and you can also cancel out one of those radii. So you end up with 65 over r, and you multiply that by the 2 to get the 130 r to the negative 1. So then we have one variable, so we're allowed to find the derivative. So we're just using our power rule here, 2 pi r squared. Remember, pi is a number, so the 2 gets multiplied to the front. After you find the derivative, you set it equal to 0. And now we just have an algebra problem that we can solve. So I'm going to start by swinging the 130 over to the other side. So we have 130 over r squared is equal to 4 pi r. And we're trying to isolate the r's, so I'm going to bring all the r's to one side and multiply both sides by r squared. And I end up with r cubed is equal to 130 over 4 pi. Now, if you're using a calculator, you put parentheses around the 4 pi in your denominator. This is an extremely common mistake that people make. If you don't put parentheses, you end up with 130 divided by 4 multiplied by pi, but we want that 4 pi to be on the bottom. I take the cube root of both sides to get the cube root of that fraction, and then with my calculator I find that r is approximately equal to 2.179. So there's my radius, roughly 2 inches. So now that we have the radius, we can use the height equation to solve for the height. So the height is going to be 65 over pi times 2.179 getting squared. And again, same thing, be careful with your parentheses here. It is okay to use the 2.179 approximation. in some contexts, it would be better to use the actual cubed root of 130 over 4 pi instead of using 2.179 because that's more accurate, but we don't need to worry about that here. If you want to go ahead and do that, you can, but then you do round to roughly the same number. So we find that the height is 4.358 inches, and now I have my dimensions for my cylindrical bucket. And you guys will see a couple of problems today in the example problems. I think questions 4 and 6 are both very similar to this one, so certainly use this as a guide. My height is 4.358 inches, and my radius is 2.179 inches. And the question was asking for dimensions, so make sure you'll always answer the question that's being asked.